We are somewhere in chapter 6, I believe. 659. We are, whoops. Somewhere in, okay. So if you have your page open, for me, it's on page 116. I'm going to mention what we're talking about today. We're going to talk about cars driving on curves. We're going to talk about more circular motion force problems. And then I want to end with fictitious forces, and I hope I'm spelling this right. For some reason, it always looks weird to me. That's just one of those words I'm not good at. So that's what we're going to try and do today, and I'm going to leave that up there. But on Zoom, I'm going to go to this just to maximize size of subscripts. Okay. Now, before we understand cars rolling on curves, I want to talk about rolling friction versus sliding friction. Okay. And to do that, I actually want to go to right here. Let's actually go over to 4. Then let me keep going over. Oops, wrong way. Right about there. There's my wheel. Okay. Get this stuff out of the way. I want you to look at this tire for a second. Right? So we're going to be talking about cars driving around, and cars have tires, right? And so we need to understand a little bit about the physics going on where the tire meets the road. In particular, I'm exaggerating this. Alan, is this showing up on Zoom where you can see the tire getting deformed?
You're like right on the edge.
Right there, got it. Can you see the tire being squished a little bit? I don't know if you can see this right here. Watch at the bottom. You see how it squishes? Now, obviously, this is a flat tire, so you can see this. Can you guys see that up there, right? You can kind of see it squishing a little bit. I want to talk about that. I know that seems strange, but that's critical to our understanding of cars going around corners. Okay? So in this case, I'm going to draw an exaggerated picture of this. This is the ground. And here's this tire. And it kind of flattens out down here. And so maybe this is our bike tire or something like that. This is the tire part. So this is my attempt to draw a picture of that. As you roll this tire, or as a car drives, its tires are going to do something like this. Now, obviously, it's going to depend on how much air you got, right? But in this case, let's assume we're going to have some squishing. So as tire rolls, there's a title. It squishes and unsquishes. Okay, very technical terms here. You could say it smushes and unsmushes. I think that's what I said earlier today. But this squishing and unsquishing is actually going to cause the tire to heat up. I think you could agree with that, right? Just think about this. If you're rubbing your hands over and over, they get warmer. If you were smushing something over and over again, it would gradually get just ever so slightly warmer, right? That's an energy loss. When you're driving forwards, you're going to lose some energy associated with this constant squishing and unsquishing. That energy loss we associate with a property known as rolling friction. We're going to say this is, this slows car down, or whatever, the tire, whatever. we account for this rolling friction. This is not sliding friction, mu static N or mu kinetic N. This is not sliding. Now, fortunately, we're going to do something very convenient for this class. For our class, assume rolling friction is negligible. So basically, I told you about this, and I'm immediately telling you we're going to completely ignore this factor. But I wanted to talk about it for this reason. If the car is moving this way, if your velocity is this direction, this rolling friction would tend to oppose your motion. Where did I put that green? Here it is. The rolling friction does matter in the real world, and it would oppose your motion just like sliding friction. Is everybody okay with that? Now, what's strange about this is sliding friction also matters for a wheel on the road. Okay? All right. Let me say one more thing about this. If you wanted to think about this, imagine if everybody put in massive amounts of air pressure in their tires, or if they had steel wheels, right? So that there's not any squishing. Like a railroad car has steel wheels. That reason is to minimize this rolling friction. So if you had very stiff wheels, either hyperinflated or made out of steel, hopefully we could make this negligible. Anyway, so that's how you might actually, if you're wondering why we could call it negligible, we'll just assume all of our wheels are hyperinflated. All right. So now, sliding friction. We have two conditions for sliding friction that we discussed already. F is equal to mu kinetic times the normal force, or F is less than or equal to mu static times the normal force. And for just a second, I'm going to go back over here. Does this work? No? Okay, I got to go back this way. Whoops, wrong way. I want to look at this wheel again. Sorry, I got to go. Gosh. Here's my wheel. Right? Now imagine you're in a car, you're driving around, you got this wheel. As you're driving, you can imagine you might start sliding too, right? Is this showing up? Kind of, yeah, I see it. Okay, so the idea is we're going to ignore the smushing and unsmushing associated with this wheel, but there's still the possibility as you try to turn, you might slide sideways. So sliding motion could actually happen perpendicular to the motion of travel. Did that make any sense? So here's the deal. When we're talking about these car problems, let's go back to the board. There's rolling friction opposite the motion that we will ignore, but sliding friction, which could be happening this way or that way, perpendicular to the velocity, is important to discuss. Is that cool? All right. When you're driving a car at 50 miles an hour, which one of these conditions do you think applies? Do you think it's kinetic friction or static friction? What do you think? Take a guess. You're driving at 80 miles an hour or 50 or whatever you drive at. Do you think and you were trying to prevent this wheel from sliding left, right. Do you think it's static or kinetic? What do you think?
Kinetic. Static.
Why do you say kinetic?
Because in that axis there is a force being applied. Like no, that's wrong.
Okay, yeah, we're not having forces this way, right? What did you say?
Static.
Oh, static. Why do you say static?
Because it's not moving left or right. Yeah.
Yeah, but isn't the wheel moving relative to the road? What do you think? Check this out. I've got a demonstration for you. Hopefully these markers are not dry. It might have been 2 years since I've used them. Please work. I forgot to check that. Come on. Oh, yeah. Oh, we got a marker. All right. This is kind of crazy. This is the axle. All right. Now I'm going to try, this marker is, I'm just going to keep pressing this up against the whiteboard and move this wheel around. And then I got to get out of the way here. Got to keep pushing this into the board. This is a picture of this wheel as I just rolled it. So notice this marker, this red marker here, is supposed to be tracing the path. Now, do you agree it's not exactly at the edge of the wheel, but it's pretty darn close? We're trying to analyze the motion. This is the path it travels. Do you agree? So, before I forget, think about just before it reaches the ground. And let me write this. This is the path of wheel. And the black marker just shows you, yes, the wheel's rolling in a straight line, agreed? So I want to look at 2 points in time. I'll call this initial and this final. I'm going to draw them up here just so we can see them better. Now, if I put this very close, approximately what direction is the velocity just before this thing bottoms out? Approximately what direction? Show me with your finger, I guess. What direction is this piece of the wheel? Look at it. Right here, it's moving this way. What direction is it moving right before it gets to the bottom?
Left.
Right here. Which way is the line going right here?
You mean down?
Downwards. Now, if I was perfect and if I could get this all the way at the exact edge of the wheels, this would be even steeper and it would be straight down. So I'm going to show you this just before it's basically moving straight down. I'll call this, actually, let's call this B4, okay? And I'm going to label this as B4. That makes this after. Just after, which way is this thing moving? So again, right, just before it's moving straight down, which way is it moving afterwards?
Straight up.
What direction is it moving? At the very, very bottom. Just before you're going straight down, just after you're going straight up, what does the velocity have to be at contact? Yes. Think about that. The wheel does not move relative to the road at this one spot. Everywhere else, the wheel is moving, agreed? Isn't that amazing? It has to do with the wheel is rotating and translating, and the combination of motion causes the velocity to be 0 at the contact point. Now, if you've ever done a burnout, maybe you understand this. I don't do a lot of burnouts, but a burnout is where you're spinning your wheels but not going anywhere. Now, think about that. If you're spinning your wheels, you don't go anywhere. It's only when the wheel happens to have this unusual property of not moving at the point of contact that you actually get the road speed matches the wheel speed and the thing actually rolls forward. Otherwise, the wheel is slipping. So when you're doing a burnout, the wheel is moving relative to the road and you kinetic applies. When the wheel is rolling without slipping, it's not slipping. This equation applies. static friction applies. Isn't that weird? When you're driving down the highway at 50 miles an hour, there's static friction between your wheels and the road. Are you okay with that? The whole point of this is this. Here's the summary. We're going to ignore this. Yes, friction opposes your motion, and it has to do with the wheels squishing and unsquishing. It also has to do with the road squishing and unsquishing. Imagine if you try to drive over carpet or something, right? Or ride your bike over mud, right? The mud would squish and unsquish. We're going to ignore that. The sliding friction is present. And even though the wheel is going really fast at its center, right? The center of the wheel is going 80 miles an hour. The bottom is not moving relative to the road. So we're going to use static friction today when we're talking about cars on curves, even though they're moving. Isn't that weird? Should we go on now and do a problem? That was that. If you want to talk more about it, we'll talk more later. Look at 659 now. Okay, let's go over this one. I think that's a really difficult topic. I'm not going to put rolling friction on the test. Okay. Let's keep it easy. Let's start with a car on a flat track. And then generally speaking, we're going to want to draw two viewpoints here. These problems are very difficult to visualize sometimes, so I like to have multiple pictures. Let's imagine we have a car going around. That's not very circular, but it's good enough. Here's the track. Let's say we have a car here. It's going this way with some speed v. Center of the circle is right here. So the dot is the center of the circular motion. By drawing this top view, we can get a good feeling for, yes, this is a car driving around in a circle. But it's important to also draw the side view. Okay? We've got this, again, this is like the center of circular motion coming out of the page. This is the center of circular motion here. Here's our roadway. And I'm going to draw the car. It's basically a block. This is my car. If you wanted to analyze this problem, does anybody have any ideas of techniques we could use to understand more about this situation? What's something we could do with this car driving around on a track?
FBD.
FBD. Tell me one force. MG. Look at these two pictures. Which one is easier for drawing MG?
Side.
Yeah, so this is easy for seeing the circle. This is easier for drawing the FBD. That's why I like both. Everybody cool with that? Okay, so we got MG. What's another force?
AC.
AC is acceleration. Acceleration is not force. It relates to it. Well, since you said AC, what does AC mean again? Do you remember?
The centrifugal acceleration
Centripetal acceleration. Which way does that point?
toward the center.
So which way is this car accelerated? Show me with your hand. I agree. Does everybody agree? This car is accelerating towards the center of the circle. Are you cool with that? Good, good. So it's not a force, but absolutely we should draw that in there. Got it. I don't want to draw it touching the object because strictly speaking, it's not a force. Okay. Anything else? What's another force?
Normal force?
Which way?
Up.
All right. It's Jose, right?
Yeah.
Okay, Jose, what's the last force? I'm putting you on the spot.
Alright, let's see.
What makes this car accelerate that way? Do you agree that if it's accelerating that way, there needs to be a force that way? Are you okay with that?
Yes.
Do you remember what force is causing that acceleration?
Step.
Yeah. Friction static, not mu is not a force. Do you agree? Mu is the coefficient, but you're absolutely right. It is the static friction. Outstanding. And that was what you were having trouble with last time. Are you feeling more comfortable with it today?
I'm getting better at learning that it's a force, not just like the AC.
Yeah. Think about this. If there was no friction, this car would just go straight off the road in a straight line forever. Agreed?
Or it wouldn't even go forward.
Well, if it had some velocity, it would be moving, right?
Yeah.
So, right, if you have some velocity, an object in motion stays in motion in a straight line unless there's some forces acting on it. So without friction, this car just goes straight off the road and into the drive-in at the In-N-Out Burger or the drive-thru. Or Chick-fil-A, you decide. Right up in there. All right, King Falafel, let's get local, right? Isn't that the local restaurant? All right, there we go. Get King Falafels, props.
Very good.
Yeah. All right. So now, because there's friction, right? The friction keeps this car from sliding off the road, and it's going to be static friction because the tires are at rest relative to the road based on all that weird stuff we talked about. This is the FBD. What do we usually do after we draw an FBD? Formulas, force equation, whatever you want to call it. Okay, give me one force equation. Oh, let's put a coordinate system on here. This direction is towards the center. This direction, is it in the direction of motion or is it not in the direction of motion? Is the car moving up and down off the road? I sure hope not. Well, that'd be a fun ride, okay? So do I want to call this tangent or do I want to call this Z? Z, right? The tangent direction is this way, or this way is tangent. This way is Z out of the page. So far, so good? Okay, let's do the forces in the centripetal direction. Sum of forces in the centripetal direction is mass times acceleration centripetal, right? What's one force in the centripetal direction? Anybody?
Friction static
Friction, got it?
equals MAC.
Equals MAC. That's cool. What about sum of forces? Z direction.
N equals MG.
Yeah, ups equal to downs because AC is 0. Outstanding. Now, in this case, usually after you draw the FBD and write down some force equations, what's a good thing to do next? Read the question and find out what we're supposed to do. You know what I'm saying? This should be automatic because anytime we have a problem with forces, we draw this and think about it, then read the question. What are we trying to do?
Answer a question.
Yeah, what is the question?
Determine the minimum turn radius for this car at this speed on the flat track.
So determine, what was it, min radius?
Yep. Turn radius.
I'm trying to find the minimum radius so the car stays on the track. What frictional condition applies? Is it F? We know it's static friction. So is it F equals mu static times N? Or is it the friction is less than mu static times N? What do you think?
Equals.
Why? What's the key word that tells us it's equals? You're right.
So the car stays on track.
That's not enough.
Or min.
Min, this is the special, like extreme. It's about to slip. It's at the minimum. That's what tells us this applies. Did that make sense? Because if you go a lot slower, it's going to easily stay on the track. If you go 1 millimeter per 100 years, you're going to stay on the track. All right. So it's this minimum. All right. Okay. Something about that. All right. So far, so good. Let's pop this in here. I'm going to make a little note here. If we try to turn any sharper, right, it's not going to work. All right. What are we trying to figure out? What are we looking for again?
The min radius.
The radius. Do you see the radius anywhere hidden in this crap?
Say AC.
What is AC? Do you remember? There was 2 ways we had for writing it. What's one of them?
B squared over R.
Yep. B squared over R. What was the other way? Somebody else? Do you happen to remember?
R omega squared.
R omega squared. Which one of these seems like a good idea for this problem? Should we grab the R omega squared or the B squared over R, and why?
B squared over R.
Yeah, why? What was given in the problem statement? B. Got it. And before we go on, was this moving at constant speed, B? I'm assuming it was moving at constant speed. Thank you. So if we read this problem, it's moving at constant speed. So, all right, now I'm feeling really good. We know V, got this. How would you attack this problem? What would you do next? What's the next step? We're looking for radius. What would you do next? This is what we have.
Horatio.
Horatio, I would do that. Do you agree we could write mu static n equals m AC? For a lot of these circular motion problems, a ratio is a good idea. Now there's other way. You could just plug in mg as well in this simple problem, but whatever. I like doing this one because it foreshadows a technique I used in some other problem, and I don't remember which one, to be honest. What drops out when you take the ratio?
N and M. Or should I said M and N?
It sounds like a really bad rapper, right? N and M. Okay, anyways, let's keep going. U static equals B rabbit? Oh, never mind. There we go. AC over G. Another trick, let the paper do the work. Don't try to do it too much in your head. All right. From here, I think you could solve for R. Do you agree? Race you to it. Go. I got to adjust some cameras on Zoom. Figure out R. Solve for R real quick. I'll try and get there too. All right. Okay. So we got here, I see mu static equals V squared over R divided by G. Mu static equals V squared over RG. That means R equals what? V squared over mu G? Yep. Now let's think. Up till now, this class has seemed almost entirely useless, right? It doesn't seem like shit, stuff you would care about in the real world, right? Think about this. Even this simple equation tells us something, right? If you know typical coefficients of friction between the tires and the road, like on a rainy day or something. Like, let's say you know when it's rainy or icy, you know this coefficient of friction. Like the Department of Transportation does have that information on file. We know G. Let's say you want them to be able to drive 60 miles an hour. This tells you how big the turn in the road needs to be. Alternatively, let's say you need to buy some land. Well, I know it has to be able to accommodate this radius of turn. Or said another way, what if I only have so much land and so much space and the radius is given? That gives a condition on the velocity. So that tells me what number to put on the little yellow sign to make sure people don't go crashing off the road, to say 30 miles or less, 30 miles per hour or less. So we can see there's a reason for doing these types of problems. We're starting to get to problems that might matter to the real world. Cool? And if you just stay with physics long enough, you will get to stuff that matters in the real world. You just got to trust me. I want to care about things that help in the real world. I do not do these weird problems to torture you just to make myself happy, right? For that, I drink beer and walk around in the woods. That torturing students does not make me happy. It's just what I'm good at. Should we go on? All right. Was there anything else in this problem worth noting? I don't think so. Oh, if you want to learn about tipping, like the car tipping over, that's a different problem. We usually handle that in chapter 12. But believe it or not, I can allude to that at the end of today's lecture if we cover fictitious forces. So it turns out if you want to understand cars tipping over, we need to learn about fictitious forces. We will do that at the end of class. All right, ready for the next problem? The logical next step is, if you want cars to go faster, what could we do with this road? Bank it, right? Sort of like a racetrack. You can imagine having a banked turf, or think about pretty much any on-ramp or off-ramp you've seen most of the time. There's usually a bank to get onto an overpass or something, right? Okay, that's the next problem. What page is it? 117, 660. I'm going to erase the board. I'm just going to be a minute. Okay, you guys go ahead and start looking at 660. Like it cleaned up. And now, if you're bored and want to walk around, talk to them, that's cool too. Will I get erased? It's going to take me like 3-4 minutes. If you want to chill, that's also fine. Actually, Alan, do you remember doing these problems when you were in 161?
Yeah, I do.
Do you have any comments for students? Like, any thoughts or something about this as we're talking? And if you could, speak up really loud so the mic picks you up. Anything that stands out in your mind, or what did you do to succeed? Because I remember you did well at this crap, didn't you?
Yeah, so I guess I just took a note of like, especially on the bank problems, I just took a note of like, because you're gonna learn about ideal speed, and you know what happens when you're below and above ideal speed. So it's kind of important to know, like, because in each case, friction is gonna point in different directions, and I think it's important to know where friction is gonna point if you're below or above the ideal speed in these bank problems. So if you remember that, then I feel like the rest of it should be easy.
So if you can get the direction of friction right, that's going to help a lot. And in order to get the direction of friction right, Alan's talking about this concept of ideal speed. We're going to start by figuring out what the ideal speed is. I'm still racing on Zoom, so you know, I don't know which board I'm on, but the idea is, and I'm still racing. The idea is we're going to first do the problem without any friction so we can learn about the ideal speed that requires zero friction. Once we know that, we get a feeling for if the car is going fast or slow, which helps us figure out if it's going to slide towards the outside or the inside, which tells us which way friction points. I agree, Alan. That's really the crux, isn't it?
Yeah.
All right, let's get to it. Let me get on the right board here. So as Alan was saying, we need to get the ideal speed for banked curve. What problem is this? 660. Thank you. bank curve ideal speed. To be clear, what does this mean? Speed which requires zero friction. So what we're first going to do is, before we try to analyze problems with friction on an angle, we're going to analyze them without. That's just like we did in chapter 5, and then we're going to add in friction at the end. I've got a top view. The top view looks exactly the same. It's a circular roadway, right? And from this perspective, we really couldn't see the bank at all, but we can at least see the circular motion. I'm just going to write center there for center, or how about circle center? Circ center. Sounds like a really terrible name for a sports arena. The circ center. All right. That's my top view. And my side view is going to look a little bit different. I think in the book, don't I call that like a rear view? But it doesn't matter. Side view, rear view, any view goes tonight. Now, do me a favor. When you're drawing this one, I want you to do two things. Make the picture a little bigger than you expect, like, you know, quarter page. And I also want you to do the same angle I do. Look carefully. Don't do a big angle. Do a skinny little angle, because we need to talk about this angle again, okay? So deliberately try to make it well under 45. Everybody got that? Otherwise, it's hard to do the next little piece that I'm going to show you. Now I got my car on here. Like that. Okay. So we're going to make a big note about this. Icy day, no friction. Said another way, we could say mu static is 0. Obviously, mu is not the frictional force, but it is related to the frictional force. It's the frictional coefficient. So maybe just to be clear, there's no friction. Similarly, we could say that's because the coefficient also goes to 0. All right. Somebody tell me one force acting on the car or the block or whatever. mg, which way?
Straight down.
mg. I'm going to label it right here just because I think that will help me later. Just put it over to the side of it. What's the other force? Somebody else?
Normal force.
Which way? Show me with your hand. Straight up?
Actually, perpendicular to the.
Normal means perpendicular. It's this way. Okay, and I want to label the normal force over here. Just please try and put your labels in the same spot. I don't normally do that to you, but today, just trust me, okay? Okay, which way is this thing accelerating? Towards the center. In this picture, it's really easy. Where's the center of the circle over here?
Parallel to the incline.
No. Center, right? Think about this. The center of the circle will be straight up. So here is center of circle. And I'm going to show you this in just a second, okay? This is not obvious. Do you agree? Think about it like this. You remember when we had this, where's my ball? I want to show you something here. Remember when we did this problem and the ball kind of traced out a cone? Yeah. Now think about this. It's the same problem. The ball is going around like this. Is that helping you visualize?
Yeah.
And so the center of the circle is right here. Look carefully, right? So we're assuming this car isn't going up and down the bank. It's basically an upside down ball on a string. Is that helping?
Yeah.
All right, is everybody cool with the center is right? So which way is it accelerating in that picture? Show me with your hand, just so I can see. Yes, excellent, excellent, excellent. Draw this AC a little bigger than you think you should, and then a little bigger. Make sure it's a big arrow, okay? I just want you to get used to that. We need this picture big. All right, you ready to learn some tricks? We need to do something with this. Do you agree the force vectors do not all line up and down or left, right exactly? We got to split something up. We have two choices of coordinate system. One of them is our standard kind of up, down, left, right. The other one that we do for these is parallel to the plane and perpendicular to the plane, like this. We have two choices. Choice 1, choice 2. Now, which one do you think is the best for this problem, in your opinion?
That's the question.
What's that? Yeah, if we're trying to learn about, what are we trying to learn about?
Ideal speed.
Speed. Do you see speed anywhere in here? Where is it? AC has speed in it. So do you agree we're basically trying to learn about AC in this problem? Agreed? And I think if we look at the numbers, I don't know, oh, in this problem, the givens were, what are the givens for this problem? Help me out. I think they told us R, theta, and V. R, theta, M, and V. Those are our givens. And what given, like, what planet do you think this is on?
Earth.
Earth, so we also know G. I haven't seen a lot of banked curves on the moon yet. You never know. All right. So these are our givens. So in this case, do you agree we basically know? Wait, did I know V? No, wait, V is what we're looking for. We're looking for the speed. I apologize. So this is not one of our givens. I apologize. Do you agree with that statement now? Sorry about that. Sorry about that. We're looking for the ideal speed. V is what we're looking for. Okay, okay. That said, which choice of coordinate system looks the best for in your opinion?
Both would work, but I would consider choice 1.
Why? I agree that both should work. It shouldn't, right? The coordinate system shouldn't affect the answer.
Yeah.
Why do you like choice 1?
Because that means velocity doesn't have to be completely work.
We don't have to split up AC. Do you see that? What about MG? Yeah, so look, I don't need to look. If I use this coordinate system, this lines up. This lines up. This does not. So let's use choice 1. And then immediately afterwards, I'm going to show you choice 2 and explain why in some cases you might want to use it, okay? So let's forget about choice 2 for right now. We'll come back to that. It does have a use. It's a very good coordinate system. Just not what we want right now. Okay, choice 1. Which vector needs to be split up?
Normal force.
Normal force. We need that angle in there, right? Let me show you some tricks, okay? I'm going to back extend this one. I'm going to extend this line horizontally, right? And I think we got it. If this angle is theta, what's this angle? This should be theta by some weirdo theorem, right?
Yeah.
That's a very technical. What's this angle?
Don't exactly know, but it's
Really? We
90
know.
minus
you know it's
theta.
theta plus
90 minus theta.
oh,
Do you agree? Think about it. There's 180 in a triangle. This takes up 90 of it. That means the other two angles share the remaining 90. So if this is theta, that's 90 minus. Or just say this plus this equal 180. Solve for that. Now, wait a minute. What is this angle right here? This is a right angle.
90 minus theta.
This is 90 minus theta. Do you see it?
Yep.
What's this angle?
Right angle.
It's a right angle, so wait, what's this one in here then?
Anyway,
Theta. Do you see a pattern happening? What's this angle? 90 minus theta. What's this angle?
Directly opposites of theta.
Theta by an alternate vertex, whatever. What's left for this one?
Opposite of 90 minus theta.
So finally, what's this one? Do you see the pattern? Every other angle is theta. Every other angle is 90 minus theta. And if you get in the habit of not drawing 45-degree triangles, you could basically look at it. All the skinny ones are thetas. All the fat ones are 90 minus thetas. Saying that again. If you make sure your picture has a skinny angle or a fat angle in it, however, right, it could be either really skinny, just not 45 degrees. Never draw 45, unless it is 45. If it's 45, draw 45. That said, if it's under 45, draw it obviously less than 45, so you can use the skinny angle trick and just say, look, all the skinny ones are thetas, all the fat ones are 90 minus, done. So far, so good? All right. Now, do you agree this is so messy, it's impossible to do any work? Let's redraw it really quick. I'll get out of the way. We now know all of that was to figure out that angle's theta. This is mg. This thing is accelerating towards the center, which happens to be straight that way. This is the z direction. This is towards the center. And now we can label these components. Is this n cos or n sine? And notice here we see an example. Finally, I wasn't trying to trip you up on test 1 when I made theta to the vertical. What happens is in the real world, sometimes angles to the horizontal get rotated in real life problems, and we have to deal with angles to the vertical to do real life work. So I wasn't trying to be a jerk. I was trying to ensure you understood this problem. I don't know if that made any sense, but here we go. Hey, this problem's done, isn't it? What are we looking for? Can you do it? Go, race you. Think, what's next? Formulas. All right, I'm going to do it over here. So I'll give you a second on Zoom and then I'll pan the screen over so you guys don't look at my whiteboard for a minute. What's up, Willow? Ooh, shoot. Right. All right, I'm going to switch over now. Is that still somewhat visible on Zoom? Okay. In this case, I wrote the force equations. I stacked them and took a ratio. The ratio is our friend today. What's sine theta over cos theta? What's AC? That B squared over R. And then we still got to divide by that stupid G. So just multiplying, I think we get what? G tan theta equals B squared over R, which if I rearrange that, B should equal the square root of RG tan theta. Still on?
No, I think it's well, I think that would work, but it's plus or minus as well, right?
True. You're absolutely right. Anytime you take a square root, we should think about the plus minus. But here we're looking for a speed. Do we usually have negative speeds? No. You can have negative velocity, but not negative speed. Good thought. Here, I didn't worry about the plus minus because we're talking about speed, which is always positive. Good question. What's another thing we could check? You just check the minus signs. Good. What else?
Yes.
Meters times meters per second squared. What are the units of a function? No units. And then we got to square root that. Do you agree that we're going to get meters per second? I love it. What else? If the radius gets bigger, what happens to the ideal speed? If you use a bigger circle, what do you have to do? Move faster or slower? Faster. If we go to the moon, where there's less gravity, G, which is the acceleration magnitude due to gravity, would become a smaller number. You could go slower on the moon. What about the angle? As you get to bigger and bigger angles, does anybody happen to know what happens to tangent theta? Does anybody know tangent of 0?
That's right.
It is sine of 0 over 1, right? Yeah, so yeah, okay, so it's 0. So basically, if your angle is flat and you don't have friction, you can't turn. Think about that. If there's no friction, you can't turn your car. That seems reasonable. What if it's 90 degrees? Then you're in the barrel of fun that we looked at, that plexiglass cylinder. Woo, 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 woo. Weird, right? This makes a lot of sense. This is the ideal speed. Now, just so I can keep working here, I'm going to go over here. So I want to emphasize this. If this whole problem was predicated on no friction, if no friction, the ideal is equal to the square root of RG tangent theta. And I don't care about capital or lowercase r for this problem. Okay. If you're going slower than the ideal speed, this is what Alan was saying is critical for your ability to do these problems successfully. Okay, so let's listen up. What's a slower speed than 50 miles an hour? Let's say the ideal speed was 50 miles an hour or 20 meters per second, right? What's the easiest number that's less than that?
10.
Rhymes with hero.
Sir.
Good. I like that one. If you were at rest, which way would friction point? Okay, now, going much slower, and how about I say, not icy anymore. Sorry, I didn't make that clear. That's my bad. Think about this. Let's say it's not icy anymore, okay? So this is going forward. We want to add in friction now, right? So everything up to this point was no friction. So let me make clear, and I didn't make that clear, that's my fault. So let's say now, what if friction non-zero? Okay, so I apologize, I didn't make that clear. So now I want to think about what happens if friction is non-zero. So now we're going to have friction. I need to know, remember Alan was saying we got to know which way it points. Well, if you're not moving which way do you think friction points? Up the plane. There'd still be a normal force. There'd still be mg. Okay. Now, do you agree if you're going just a little bit above zero, this should still be true?
Yes.
So this helps us understand if we're going at slow speeds, you're still going to accelerate this way, but there's friction up the plane. And again, that's for V less than V ideal. So if you're going faster than V ideal, we're still going to have our incline. It's still not icy. Sun came out. Great. There's still going to be this block. There's still going to be a normal force. There's still going to be mg. There's still going to be acceleration towards the center. If you're going too fast, do you think you tend to go to the outside relative to the curve, or do you tend to go to the inside relative to the curve if you're going too fast? So you tend to move to the outside relative, so what does friction have to do? Down the plane. So I'm going to say down the plane. I'm assuming that's what you meant?
Yes.
Because to the left isn't correct. Do you agree? Yeah. But if you're tilting your head, then to the left would be correct. Which I think that's what you were doing. Everybody cool with that?
Yeah.
The rest of the problems on this page will address these scenarios. Now, do you remember I said there's different choices of coordinate systems you might want to use? Now we can see the advantages of choice 2 that we didn't use. Now look, if you're trying to learn about AC or V or R, the normal coordinate system is good because AC, you don't need to split it up. What if I wanted to learn about the coefficient of friction? Which one of the terms here would contain the coefficient of friction? F. What coordinate system do you think might be useful if you wanted to learn about F? The rotated. So what we want to do is in order to understand this problem, I want to redo the previous problem with the rotated coordinate system and show that it still works. Boring, but useful. Got it? Then you guys can do these ones on your own. That said, I need to erase this now. Is everybody okay with that?
Can I still write?
Yeah. You need a second? Actually, I could probably do it right here. I'm just going to work over here, but I got to move my camera a little bit. How about that? You guys see all right? Just like you guys are all on that side today. Guess we know who's ace in this class, right? Okay. This is what problem was it? 660? This is only going to take a second. Okay, and please, I know I need you to draw big again. Okay. Normal force right here. mg, label it right here. Now, am I still on right here?
Yeah.
Okay. Draw that AC arrow a little bigger than you think. And then a little bit bigger. Because we're going to have to split up AC now, right? We're going to use our rotated coordinate system. So that allows me, am I still on right here?
You're right on the edge.
Right on the edge? Okay. Is that good? Still good?
Yeah.
Thanks, okay. So now, if you recall, this angle down here is theta. What's this angle? Is it theta or 90 minus?
Theta.
Theta. How about over here? If this angle is theta, what's this angle?
Theta.
This is also theta. Is everybody okay with that? Some kind of whatever, okay? So now, I'm gonna split up mg. Just look at the screen here. Look, give me your eyes for a second. Why is this incorrect?
Parallel to the.
It's not parallel to the coordinates. Remember, the original vector must be the hypotenuse. The original vector has to be opposite the right angle. What's this component right here? mg
Sine theta.
What's this component right here?
Cosine theta.
Yeah. Now, do I need to split up the AC vector? Is this right? Is this right or is it wrong? Wrong. Why?
It's not parallel to the,
Yep, you got it. This side should be labeled AC sine or AC cosine.
Cosine.
Adjacent gets the cosines. Opposite. Could you write force equations for this? Let's do it. Now, what names do we want to give to these? Sometimes I'll call this perpendicular or perp. This is perpendicular. So the symbol is like an upside down T. That makes this the parallel. Sometimes I'll use just para. So we're going to be using para and perpendicular now. Okay, so somebody give me the sum of forces perpendicular. For no good reason, we'll do perpendicular first. What's one force perpendicular?
Acceleration.
What's that? I want a force. Acceleration is not a force. What's that? Give me a force that's in the perpendicular to the plane direction.
Mg cosine theta.
mg cos, positive or negative? What's another one? Can I just say n equals mg cos?
Yeah.
No. Is the acceleration perpendicular 0? I gotcha.
You got me.
Look, this equals this if acceleration perpendicular is 0. That's where people screw up this problem. Got it?
Yeah.
This is no longer equal to that because it's accelerating perpendicular to the plane.
Okay.
And the combination of this acceleration plus that acceleration adds up to straight to the left. Weird, right? Now you know why I'm doing this, okay? It's going to be what? Plus AC sine theta or minus AC sine theta?
Plus AC.
Does that equation make any sense at all? What's the other one? Force para? What's that equation going to be? Somebody else. What's a force that's parallel?
Mg sine theta
Plus or minus?
plus.
Anything else para? Right now, no. Agreed? So all this equals what?
And the AC cosine theta.
Yep. Got it? So now you know how to do either coordinate system. Feeling okay on that? And to be clear, how are the other problems gonna change? You're just gonna add in some friction. I know how to do it. You gotta make sure you know how to do it, so make sure you do a couple of the other problems on this page. Got that? And you will have this dialed in. Now, from this point, there's lots of tricks. If I try to solve for n, hey, it's pretty easy to solve for n in this equation, so that's a good thing. If I need to get the normal force, but whatever. All right, good enough on that problem? Woo!
That was kind of-
It is kind of tricky. And I think that's a good spot to take our break, because it's been a long haul. Ready for that break? Okay, let's call it. We'll take a break and then we'll come back and do some more. Woo. Oh my goodness. Oh, I should have been erasing. I just sent you the lab manual. Sorry that took so long. I'm gonna erase the board and then be ready to go.
I did have one question real quick.
Yeah, I'm listening.
So there was one part in the test, the first one,
Yes,
that I had no idea how to do,
okay.
but now that I looked at the solution, I just, I think I was missing a part of the workbook that I just didn't understand.
Okay,
It was the one of the particle with the.
I'm still erasing on Zoom, by the way. Okay, go ahead.
Was a particle at function of time. Additional particle.
Oh, okay, okay.
And,
So the separation of variables crap?
I think that one actually was two-stage problem,
Oh, okay, okay.
because it moved back and forth.
I'll have to, you know what? We gotta sit down and look at it.
Yeah.
And if you know what we could do is, I'm sure in lab tomorrow, if you do all the FBDs in advance, we'll have plenty of time to look at it.
Yes.
So, I should mention for this class, it's crucial that we get out of lab on time tomorrow. I'm supposed to meet with a couple of physicists out of town tomorrow night after lab. So I gotta get on the road tomorrow night. So class is ending at 8:35 sharp. So if you can, basically, all you gotta do is, the email I just sent, or the Canvas announcement or whatever, I sent the lab manual. On page 4, there's a checklist saying exactly what you're expected to turn in and exactly the formatting you're required to use when you're turning it in. And one of the things you're supposed to do is draw a bunch of FBDs and write a bunch of force equations. And they're basically workbook problems. So you've got the answers somewhere, and I think I alluded to it even in the handout. So if you can have all that stuff ready, what we can do is tomorrow you'll do the math, or you'll do some measurements, plug in some numbers, crank out the lab, and be done. And it should be hopefully educational, slightly fun, if you have all that kind of boring prep work done already. So I guess that's me trying to sell you on, please read the lab manual ahead so that you have fun tomorrow instead of being stressed, knowing that we have to leave at 8:35 sharp.
I have a question.
Yes,
So in this regard to lab.
sure.
So are we going to be assigned up for one project per group, or are we doing all of these?
So there's going to be 3 projects and they should each take about 45 minutes.
Okay, fair enough.
Yeah, yeah. And the idea is, so you'll have 3. I wanted to do a lab. I had to throw out the oral presentation. So this is just one night, turn it in. Got it?
Got it. Thank you.
Yeah. So if you're turning these in at 8:35, right, you don't want to be stressed out not having things done. But if you have the force equations done already, it should be no trouble to get this done. So yeah, is that clear?
Yeah.
Yeah, yeah.
Thank you.
Question?
I had a question about the ideal speed.
Yes.
So in that problem we did, there was no friction, right?
So that if you have no friction, you get the ideal speed. Any faster, you go to the outside of the turn and crash. Any slower, you go to the inside and crash.
So did we get the ideal speed when there's no friction?
Yes.
Or, okay, so the ideal speed, like in the real world, would have some friction still?
Oh, so here's what you would do. What you do is, imagine you're working for the Department of Transportation. You want to take the worst possible scenario, an icy day where there's very low friction. And then you say, okay, what's the safe range of speeds here? So you could first set the friction to 0 and get the ideal speed, and then say, okay, what if I actually have 0.1 for mu? And that tells me, okay, if I have 0.1 for mu, that gives me an upper limit on the speed and a lower limit on the speed. And then you try and adjust the bank such that that gives a reasonable, safe range of speeds for the worst possible conditions on the road. And then if it gets even worse than that, you close the road and tell people to wait till tomorrow. Good?
Yeah.
Yeah, yeah. And so in practice, in the real world, you get these ranges, because if the friction's not 0, you get an upper and a lower limit. And if you want, I believe that's question. I think the next problem asks you to figure out the range. So 6.61 does exactly that. First, it says get the ideal speed, then get the max, and then the min. Cool?
Yeah.
Outstanding, outstanding. Other questions?
One slide.
Yep.
Okay. So I was thinking, since we have so few people right now, are we still gonna do groups or are we gonna?
Yeah, there's a bunch on Zoom right now too, and people,
Oh, okay.
and you know how it is. When you have the offer of watching it on YouTube later, everybody's like, oh, I'll just watch it later, and then doesn't, and then fails the course. So, but yeah, they'll show up for lab tomorrow.
Alright.
Yeah, so they'll be there. And then what we'll do is we'll just get into groups of 3 tomorrow. We'll handle that. Good questions? We'll handle it in lab. Good?
Yeah.
Yeah, and I'll make sure everybody's got a partner. All right. I want to talk about 664, page 118, 664. Now, we're going to keep this simple because I don't want to talk about rolling over a hill, but it's very similar. Imagine we have a road like this. We talked about going around a turn. What about going over a hill? And in particular, move this over. So this is supposed to be the road. Just so you can kind of see some character there. This is a cool trick that always works. What we're going to do is we're going to say, look, this road shape is not circular, but I do know if I had a block right here at the top, I could model this portion of the track as being circular. I could make this one portion is approximately circular right there. So at any one instant, I could figure out the circle that best fits this road. And if you took a calculus class, maybe you remember something in your calculus class that had to do with the second derivative being radius of curvature. If you don't remember that, that's cool. But basically, you can use calculus and figure out this radius. So let's say we have some radius of curvature here. Now, I want to point out the block is actually, the mass of the block is centered here. Probably right in the middle of the block. For now, we're going to assume that. So notice the block is actually going in this radius of circular motion. Did that make any sense at all? The block has this radius. So it turns out up until now, we've kind of been ignoring the size of objects. In this particular problem, I believe they say this height, the height of this block is, I think, the radius of the circle over 4. So we're going to assume that for right now. Am I losing you with these pictures, or does this kind of make sense?
Oh.
Yes?
What I would have done is like have the same big R over there, but plus like something else.
Yeah, and let's figure that out. So do you agree little r is equal to big R plus something else?
Yeah.
What's the something else? You
It's the
just
height-
said it.
The half the height of
Yes, r equals the radius plus half the height. Well, in this case, what does that turn out to be?
the
What's
height
half of r over 4?
R over A.
Which is? You just did part A. That's part A, is figure out the radius of circular motion. Is everybody okay with that? Now, I don't know if you know this, 1/8 is about 12.5%. Notice if we ignore the height of this block, all of our answers are going to be off by maybe 12.5%. That's kind of a lot. Now, so if the size of your block matters, you can do this. Hey, listen up. I'm not doing this to you on test day. Got it? I'm going to say on test day, everything's going to be negligible size, negligible size, negligible size. Maybe when we get to chapter 10, that will be different. But for test 2, I'm not going to try and mess with you on the height of these blocks. I just wanted to show you how to handle that. Everybody cool with that? So, all right, just trying to be clear that I feel it's important to see it. And now that's all we got to do. Let's talk about this. If we want to understand this, and this thing's moving this way, all right? So for this problem, you can imagine this is a car driving over, or in this case, you can imagine there was a block here and I flicked it. So imagine there's a block and I just flick it and it goes up, all right? They're obviously related problems. Let's just do the simple one, flicking a block so it slides. If I want to understand something about this block, what could I do? What have we been doing every problem?
FBD.
FBD. Let's do that FBD. Somebody give me one force acting on the block at the top.
FBD
Which way?
down.
What else?
Normal force going up.
Normal force. Roads push upwards. They don't pull you down unless they're magnetic.
Isn't it better to say they push perpendicular?
Yes, you're right. They push perpendicular to the surface. Excellent. Walls and roads push perpendicular to their surface. And ropes pull. All right.
Velocity.
This is velocity
not
a
a
force?
No.
No, excellent. You caught it. We're going to assume constant speed here in this problem. Is that correct? Just double check. Does the problem say constant speed?
No. Doesn't say.
It says, suppose you're told to speed the velocity.
Oh, okay. It says the speed is v. If it says the speed is v,
It should be constant.
it should be a constant. So that's implied. That was tricky. The problem says it goes at speed v. If it goes at speed v, that's a set constant speed v.
It is.
Okay. What is the force that pushes the car or the block forwards? We don't have one. Once you flick it, it's got momentum. You don't need force to keep moving. So I was trying to trick you. You were good in that you didn't answer something. That was a good move. In this case, just because you're moving, you don't have to have a force to move, right? You need to have a force to change your motion. But at this point, we've got these forces, which are good. What about backwards? Can you think of any forces that might be backwards?
I want to say static,
Friction? Some kind of friction? Does this problem say anything about friction?
I don't think so.
I think it says frictionless, doesn't it?
Yeah.
Yep. Okay, so we could have air resistance, but we're going to ignore air resistance. When I say constant speed, is acceleration zero?
Yes.
No. If you're moving in a straight line and you say constant speed, acceleration is
That makes
zero.
more sense.
What's the acceleration when you're moving at constant speed in a circle?
AC.
AC, which way?
With the center.
Trick question, gotcha. Now, when I say constant speed, one component of acceleration is zero. Which component? Has zero. I'm going outside in the sun. I'm staying out there without sunscreen. I get a tan. Okay. Good. Excellent. Yeah. Remember, constant speed tells us this. So that's probably the one you were thinking of. A component of acceleration is zero, but we still have a component towards the center, right? Just before going up, just after going down, the velocity changed downwards. The speed didn't change, but the velocity did because the direction changes. Good? All right. Somebody want to give me this force equation? Anybody?
N minus MG.
And
I heard N minus mg. What does it equal?
MAC.
Nope.
Should be opposite, right?
Yeah, it's like these have to have the same sign, so you would say,
MG minus M.
I forgot to write the negative.
yep, negative, or, okay, Peter, what were you saying?
mg minus m.
So you're saying down, if down is positive direction, you said, what? I forget, say it again.
Mg minus n equals mac.
That's also correct. So we see if you call up positive, you got to remember that minus sign. If we call down positive, you don't have to remember. So the way I check it is, look, this and this had better have the same sign. They do. That's my way of checking it because it's easy to forget a minus sign. Good? Okay, at this point, we usually reread the question and see what we're trying to learn. What up, Dom? Okay, let's think about this. Let's solve this for the normal force. Normal force is equal to mg minus mac, agreed? Take a second. All I'm doing is I've taken this equation and rewriting it down there. Everybody okay with that? Think. As you go faster and faster, what happens to the normal force? Does mg change?
No.
Does mac change? As you go faster, does AC get affected? What happens to AC?
It gets smaller.
What's the equation for AC? Let the equation guide your reasoning. AC equals,
B squared times divided by R.
as V gets bigger, what happens to AC?
It's one.
It goes up.
Oh.
More V, that's more V squared. This is a bigger number. If you use 4 instead of 1, you get 16 or
Put
something.
it backwards.
That's right. So now help me out. This thing's not changing. As you go faster, this term gets bigger. What happens to the normal force? It goes down. You're subtracting more and more as you go faster. Is there some logical limit? What happens if you go too fast?
Fly.
Yes. If you fly, what's the normal force? 0. Lose contact. So how about this? I'm just going to squeeze this in right here. Sorry, you guys can't see it, but if go too fast, lose contact. So I'm going to say that again so you can hear that. If you go too fast, lose contact. If you lose contact, what happens to the normal force? I'm going to write that up here so you can see that. Then I'm going to rewrite this equation and I'm going to change my. Now I'm going to switch boards. Okay. If the normal force goes to 0, what do we learn? What drops out? Okay, how about I rearrange this first? Do you agree that's mg equals mac? What drops out? M. You can divide every term by m at this stage, agreed. You can divide 0 by m, mg by m, mac by m. So notice the mass of the block doesn't matter in terms of losing contact. So you can have a light object or a heavy object will lose contact. How can we find out about the speed? Yep. Yep, RG. Do the units check? They look good. Is this a minimum or a maximum speed based off what we've been talking about?
I think it's a maximum.
It is. If you go any faster, you catch air or go flying,
Yeah.
right? So we see in this case, set n goes to 0 gives the max equals square root RG. And remember, technically, this little r should be, what was it, 9/8 big R or something? Who cares, right? Now, think about another problem we did. In particular, something I made Peter do. What did I make Peter do last class that was kind of possible making a mess? Yeah. Now, in that case, do you remember we did this? In that problem, was it a minimum or a maximum speed at the top? Do you remember? That was a minimum. If I go too slow, the ball doesn't make it, right? So in that one, you can go hella fast, right? It's not, so in that problem, why is it different? Well, give me a second. Remember the water on a tray or the ball on a string? What does that FBD look like? Give me one force for the ball on a string. What's the other force?
Say FG.
Yes, and they're both downwards. In this problem, everything was pointing downwards. We set t equal to 0, got the minimum, right? The minimum speed. Notice if the arrows point in different directions, up here in this one, we had a normal force up, an mg down. They're different scenarios. They give different max or mins. But in the end, it's the lose contact condition or tension goes to 0 condition. It's very similar problems. It's just in one problem you get a max, and one problem you get a min, but it's an extrema in either case. Just a sec. Is that kind of okay? There's different free body diagrams. That's why sometimes you get a min or a max. Yes.
Are you also covering how to get the min in the switch scenario?
We don't, well, the minimum speed to go over the hill is different.
Yeah.
Right? That depends on the height of the hill. That's chapter 8. That's 2 weeks from now.
Okay.
Or actually next Wednesday. Good?
Yeah.
All right. And this one, the maximum speed would correspond to what? If I keep going faster and faster in the real world, what's limiting this problem? Why can't I go infinitely fast?
The tension of the string.
Yes, at some point the cable breaks. So there's a rating for this string, which would give you a maximum value of tension. That free body diagram would help you figure out the max speed. And I think there was a problem in chapter 6 like that. I just don't know the number right offhand. Cool?
Yeah.
Yeah. Okay. All right. You ready for some fun ones now? You guys, there's only what, 6 of us? 1, 2, 3, 4, 5, 6, and a couple of, man, this is like the most brain pop, right? Oh my gosh. 2 instructors and a learning assistant for 6 students in here live. That's hilarious. All right. Let's look at some of these demos over here. You guys may want to just come over so you could actually see them a little bit. I don't know if you want to bring your, because here's the deal. Let me put it like this. I need to like show you some stuff and then work on the board. You may want, I don't know, if you're happy where you're at, that's fine. But if you want to see them better, do whatever you want. If you're going to scoot over, you may want to bring your materials over. And we're going to look at 6.66. All right, so look at 6.66. I'm going to erase the board really quick. 6.66 is the next problem. So take a second to read 6.66 while I'm erasing. I promise I'll be right there. Still erasing. No. Okay, 6.66. And that is. Okay, Alan, I'm gonna use yours. I didn't see that thing. We'll look at this one here. Good. Get this out of here for a second. Look at this one. There we go. Can you see the strings okay, Alan?
Yeah.
All right, so here's the deal. I don't know if you can see this, but there's a bunch of nuts on here. Now, there's actually, if I rotate this ever so slightly, on this side, we see two equal-sized nuts at different radii. On this side, I have equal radius, but different masses. Let's focus on this side right now. So kind of ignore this one for right now. Let's focus on these two. I'm going to pull the string very gradually. Why do you think I said very gradually? Tangential acceleration is approximately 0. So we're going to have only AC. This thing's going to spin in a circle. Which nut will hang outwards at a larger angle? What do you think? Take a second to think about it, and then we'll pull the string. Which one of these nuts, the big one or the small one, is going to have a bigger angle? Go ahead, take a second to think about it.
Can we guess or can we just-
Sure, guess. What do you think?
I'm guessing it's gonna be the heavier one,
Why?
because that one has a bigger component of, I think it's in the space of the G cosine or something like that.
Okay, so it's heavier, so you're saying it's going to need more tension.
It's gonna exert more tension.
Well, you need more tension for the larger. That is absolutely true. We need more tension for the heavier mass. And you're saying there's some trig which may affect that angle, huh?
Yeah.
So that's your reasoning. Anybody else? Anybody think it's the little one? Why do you say the same? Because it's my class and I always trick you. And that's the right answer.
Yeah.
Let's take a look, all right? We could, here's something that I'll say it like this. Have you noticed that in many of these circular motion FBDs, the mass drops out?
Yeah.
This happens to be one of those problems. If you weren't sure if the mass matters, we could draw the FBDs and see if the mass drops out or not. So now, here's another way to do this. If you're building an amusement park ride, you don't want the adults to smash into the little kids. So it turns out they did the math on this and discovered it doesn't matter whether you're a kid or an adult on this ride. It's going to work. Okay, you ready? Do you agree they're at the same angle? Oh, shoot. Yes. They're bumping into that. We should have moved it out. Let me try that one more time. But they were at the same angle until they started hitting the screen. Now this one's gonna look kind of crazy. Watch this. Isn't that kind of fun? So obviously, this is another reason I have to do this gradually. Oh, whoops. Oh, crap. Don't have to be hitting the head. Okay, let's try it one more time. Sorry about that. Settle these down. This time you could watch the other one too. In this case, how about this one that's at a smaller radius? Small radius versus big radius. Do you think they'll have the same angle or not? What do you think? If you're at a smaller radius, what happens to AC? What happens to the forces? I don't know. Let's just look. Then we'll do the free body diagram. Ready? Do you agree the inner one has a smaller angle and the two that are at the same radius have the same angle? Isn't that kind of cool? Is that showing up at all? All right. Let's look at the FBDs real quick. Let's go to the board. You guys get your paper out. Thanks, boss. All right. Okay. So now in this case, where were we? Where were we? We're doing 6.66. Okay, we've got this weird thing that looks like this. It's rotating. In this one, I actually like using AC equals R omega squared. Now let me tell you why. When this thing rotates, do you agree all the different masses have the same RPMs? They're all rotating the same number of times per second, but they don't all have the same velocity. So in that type of situation, I like to do AC equals R omega squared. And typically, right, in an engine problem, you might say, oh, I have so many RPMs. That leads you to how many radians per second. All right. Somebody give me one force acting on the ball. Tension. Does it push or pull? Ropes pull. Okay. In this problem, was this angle theta right here?
Yes.
So that was the angle we were kind of looking at there. Now, in this problem, this is tension. What's another force acting on the ball? mg, straight down. You got that one unlocked today, man. Right? You got it though, right? Hey, what's any other forces? Is it accelerating? It's moving at constant speed, right? Remember, we said gradual speed up. If you have a gradual speed up, that told us A tan equals 0. If A tan is equal to 0, that's fine. We know that there's a centripetal acceleration. You could use V squared over R as well. Either one of those would work. What direction is towards the center? Show me with your finger.
It changes, I guess.
No. Oh, I see what you're saying. As it goes around. Yeah, that's true. At this instant in time.
Yeah.
At this instant in time, you guys did it. Do you agree it's straight there? Again, the motion is this complicated circle like that. And this was, it's going in and out. It's kind of like the conical pendulum. All right. Oh, shoot. In this case, whoops, this is AC. What coordinate system would you use? Straight up and down or rotated? You call it. Are you going to use a normal, or are you going to use a? No, look at this. Which coordinate system requires us to split up the fewest number of vectors? Up and down, because these two don't need to be split. You see what I'm saying?
Yeah.
Now, would the other way work? Absolutely. Is it harder? Absolutely. Well, what's if this angle's theta? What's this angle? Theta. Skinny triangle trick. Don't draw 45s. Okay. At this point, do you agree you could write some free body diagrams or force equations? What's this component right here? T. Seems easy enough. What's the radius? That's the problem with this weird contraption. It's this distance, which is R. What's the length of the string called? L?
Yes.
So what's this distance right here? Opposite or adjacent? Opposite. L sine or L cos? You got it. So in terms of these two, what's the radius? Money. You got it. The rest of the problem's easy. Agreed? You just do some work and read what you're supposed to solve for and solve for it. Ready for another fun one? We're doing rapid fire, right? Look at 6.67, the water spinner. There's Dom. I got Dom right in there. Sorry, Dom. Whoa, whoa. I got the top of your head. Sorry, Dom. It's right behind you. I'm coming right behind you there. Okay, we're going right here. All right, water spinner. Now, I love this problem. But in the interest of time, I'm going to give you a heads up. Not on the test. Understood? Now, for me, I just think it's beautiful. And sometimes, to keep myself sane, I need to show you something that I think is beautiful. And this is it. So if you are passionate about understanding this, great. Read the problem and do it at home. If you do not care, check this out and it looks cool. A tan is approximately 0 if I pull this gradually. Watch the shape. See it? Oh yeah, let's go for it. My bad. It's gonna hit me. Whatever. Do you see the parabola? Is there any practical use for this?
A spinning rocket with fuel inside of it.
Oh, maybe. I have no idea. That wasn't the application I was thinking of. Look below part E. Turns out you can do this with mercury and make a mirror and make a giant spinning mirror out of mercury that looks straight up called a zenith telescope. You can make this thing hella big for about $10,000 and it's got extremely good resolution per dollar spent. So this is a trick that astronomers will use. Now they use some other tricks like basically they have a DC motor to keep it spinning at the right rate. And instead of having this huge trough full of mercury, what they'll do is they'll have basically a shell and it's just a very thin coating, but basically that's a way to make a mirror and you have to keep it spinning to do the astronomy. Isn't that wild? I think it's cool. It made a big mess and it did, and it's not on the test. All right, what's the can I flip the page? Let's look at 6.76 real quick. Man, that was cool. No, it's just food coloring in water. We put a little color in there just so it stands out and it looks cool, and that's it. But that's a pretty cool problem, I think. I don't know. I thought it was really neat. If you're curious how to derive that, you do an FBD, you relate the slope to a tangent line, you use calculus, blah, blah, blah. Hey, Don, could you do me a favor? Scoot something somewhere. That's the one I want. Yeah, that's, yeah. Okay, Don, we want to take that. Okay. Now this one's kind of crazy. Am I still on screen now? Oh no, I'm not. I'm a little low. So I'm gonna fall. There. Okay, with this one, check this out, and I want to point out something very carefully here. This is a weirdo contraction. I like this problem. Now, probably can't see this very well, but there's actually two different strings here. You see that? There's one that's tied up here and one that's tied down there. What I'm going to do is I'm going to pull this thing. Again, very gradually. A10 is 0. Oops, that's super gradually. It's going to settle in. Now look at this thing. There's two strings here. How many forces are acting on the ball right now? Let me try that again. Let's just do this. Give it a second. It's stabilizing. It's kind of stabilized. How many forces act on the ball? Give me one force that acts on the ball. MG. Ah, he took your force. What's another force that acts on the ball? Tension, which one? Okay, so maybe we call it tension 1 or tension upper. And let me just hold this out here so you can see this. What's another force acting on the ball? Tension 2 or tension lower. Is this ball accelerating if it's at constant speed? It is, because circular motion, acceleration towards the center, even if it's at constant speed. You can do this problem, do an FBD, that's there. This was on the test once. It's a good problem to practice. It's basically a variation. A lot of these problems only have 2 forces. This one has 3, right? So that's a good way to mix it up. All right. So far, so good? Let's see where we're at next. Oh, yes. Go to page 120. 120. I'm just getting organized here. I may need somebody to help me out a little bit. Let me get some of this crap out of here. Here's what we're looking at. If you got to get out of here, that's fine. We still got 15 minutes or whatever. All right, this is kind of a janky thing here. All right, can you see that all right on Zoom, Alan, a little bit?
Yeah.
Okay, now it's a little bit tricky here. I'm probably going to need, do you want to come up and just help me hold that thing?
So right here.
Yeah, we're going to, the stopper, take the stopper out, but hold the cart. Okay,
I see what you mean.
and then stand out of the way, kind of like lean way back. Yeah, there we go. So what we can do here is I want to look at this thing and actually put the stopper back for a second because I'm going to babble for a little bit. Sorry. Okay, and then you can just step back for a second. All right, and you don't have to hold it right now.
Okay.
You're good. Whoa,
That's why.
okay, I will take that mask off for a second. Sorry about that. Okay, there we go. All right, sorry about that. There we go. Okay, so the idea is when I put this mass on here, we let go of it. This thing's going to start accelerating. And then I'm going to get in here for just a second. Imagine this thing is accelerating. As this accelerates, what direction is this ball going to move relative to the earth? When I let go of it, which way does the ball go relative to the earth?
Stays in place for a little bit,
Okay, then what?
and then goes to the right.
It's going to go this way. Do you agree? It's attached to this thing. The whole apparatus is going to get pulled that way. Now, to be clear, it's going to sit there and then it's going to kind of move like this, right? So at some point, at the instant you release it, it's got so much inertia, it almost tends to stay in place. And then this thing's going to launch out, and then there's going to be tension and it's going to be pulled along. Do you agree? But ultimately, this ball is going to move forwards or this direction relative to the earth. Which way does it move relative to this Play-Doh that I'm putting on top? Moves the other way. This is a weird phenomena that you have experienced in the real life, in the real world. You feel like the ball moves backwards, but what's happening is it's moving forwards, just not at the same rate as you. Let's run this thing. All right. So now go ahead and take the stopper and hold the cart for me. You can leave the Play-Doh on there.
Okay.
I'm gonna jack up this mass. I want you to watch the motion of the ball very carefully. Can we see that at all?
Yeah.
Do you want me to zoom in on it? Would that be better? I want to get just the first second of motion of that ball there, so let me zoom in. I want you to watch this ball, and in particular, notice we should be able to see an angle there. Okay, Mark, let it rip whenever you're ready. Go. I hope you were able to see the ball. Did you see it? And we saw that it moves forwards relative to the earth, but backwards. Let's give Mark a round of applause. Okay, I know this seems silly. I'm passionate about you understanding this. I don't know why. I guess I'm crazy. Thank you. Okay, so what's happening here is we see the ball being pulled like this. What's one force acting on the ball? mg. Yeah, you got it. You reclaimed the throne. Nice. This one is tension. I'm just going to speed this up so we can get out of here. Are you okay with that? We got a T, what is this? T cos. And this component here is T sine theta. Is everybody okay with that? We saw this ball as accelerating this way. If we wanted to, we could do a free body diagram on the ball cart system and learn about the acceleration is m1 over m2 plus m1t or something. Anyway, whatever. I forget if it's m1 or 2 on top. I'm going to write down the force equation. Just give me a second here. Do you agree in the x direction? That's the force equation. Just don't overthink it. Is everybody cool with that? Now watch me. Just give me a second and watch. Please just watch for a second. Okay? It's only going to take a second. I can rearrange this equation like this, right? Now wait a minute. I'm just going to randomly write some symbols next to this for no good reason. I'm going to pretend this is the sum of forces in the x direction, and it's equal to mass times acceleration in the x, but I'm going to pretend that the acceleration in the x is 0. In theory, this equation looks like a force equation. And remember how all day you keep saying A is a force, A is a force, A is a force, when it's not. A is not a force. It relates to the force, but look at this. This is a pretend. This is a fiction. It's a lie. This is a fiction. And in particular, this is a fictional force, or sometimes called fictitious. And you may be saying, why is he lying to us? I'm literally lying to you right now. MA is not a force. Turns out there is a use for this, and I'll explain it in just a second. Look, this is equivalent to the following free body diagram. There's tension here. There's mg down. What? This would have to be a force that has size ma pointed which way? Help me out, right? This is T cosine theta. This was theta. This is T sine theta. Which way would MA have to point if this was a real force? That way, right? Because it's negative. This is a cool trick. What you can do is you can say, look, I know this ball is accelerating this way, so I'm going to tell you it's not accelerating at all and put a force, MA, pointed the other way. Now you may be saying, what good is this? It turns out we're going to learn a branch of physics known as statics. There's a whole class in engineering called statics, taught by that bozo. And he's going to tell you there's probably one problem you do this, and I'm assuming it's the car tipping over problem. I don't know, maybe he doesn't use it at all. But the idea is, imagine you have a car driving around a flat track. Well, I could say it's not accelerating, and yet there's mg down, There's a normal force up. There's a frictional force toward the center. We know it should be accelerating this way. So that means there's a fictitious force this way. I'll call this force fictitious, MA. And now I could treat this problem as at rest, and I could use what's called statics techniques. We'll discuss this more in chapter 12. This, I think, can help you understand why you keep thinking you're pushed to the outside. We perceive this fictitious force in the real world, even though it doesn't exist. When you accelerate towards the center, we feel that as a push to the outside, even though we're not pushed to the outside. We're pushed towards the center, and because we're pushed towards the center, we think we're being pushed towards the outside. Is that good enough? All right, one more fun one, and then we're done. Got down there, move up here, over, just down a little bit. Okay, last one. This weird contraption. Approximately on. Pretty close. All right. I've got pool floats in here, or fishing floats. These are peanut butter jars, inverted and filled with water, with what looks like a little bit of peanut butter residue still left in there from when we cleaned it. My bad. Or maybe that's glue that fell off. So there's some chunks in here floating around. Just ignore the chunky floaters, all right? That said, I'm going to accelerate this thing very gradually with a small A10 value that's close to 0. My question to you is, once it stabilizes, we've seen this all day, it takes a second for these things to stabilize. Once it stabilizes, what should happen to the pool floats? Are they going to go towards the center? Are they going to go towards the outside? Are they going to explode and tell you you get an A automatically? One of those three. What do you think? Any guesses? Anybody want to take a guess? Take a second to think about it.
I feel like this is a trick question, but
Of course it is. I'm asking. I try to ask these because I like the trick questions because it forces you to think. The other thing that I want you to do when I ask these is I want you to learn to become confident when you do know the answer. I don't know if you've noticed, I sprinkle in some tricky ones and some that are easy. And I'm trying to train you to be confident in what you know, but not overconfident, right? And I don't know if I'm succeeding in that goal, but that's why I do it this
you
way.
are, because the reason I'm answering right now is I don't know.
Okay. Any guesses? In or out? What do you think?
I think it would lead towards the outside.
Okay. Let's see. Ready? Now again, you got to let it stabilize. This one I kind of have to go kind of slow. Again, this is give it about 30 seconds after I've done with the string. You see it already happening? Give it a second. Now what's happening is the water inside is swishing about and becoming basically a couple of vortices. But just give it a second. Just trust me. It takes about 20 seconds, and then we'll look at it. You see them starting to stabilize now?
Yeah.
Where are they starting to stabilize?
Center.
Towards the inside. Do you see that? There's a name for this device. Does anybody know what this device is called?
I feel like it's something similar with DNA.
What do you mean with DNA? A
Uh,
centrifuge. This is a centrifuge. You spin something, the light stuff goes to the inside, the heavy stuff goes to the outside. Think about it like this. Just give me a second. Try to stay focused and then we'll be done. Do you agree that pool floats tend to point the opposite way of gravity? Gravity points down, the pool float goes opposite that. Now, when I spin this, I'm creating artificial gravity. It's a fictitious force. There's an acceleration towards the center, which is equivalent to fictitious gravity towards the outside. Pool floats oppose the regular gravity and the fictitious gravity and go towards the inside. Isn't that fun? These fictitious forces are very confusing. I do not recommend using them, right? Unless you are good at what you are doing, and basically you are not good at it until you learn how to do statics. So don't practice with fictitious forces until we get to chapter 12. I was talking with Matt, that professor up at Cal Poly. He says, I just don't do it. Students have enough trouble with regular forces. Why would I layer in fictitious? The only reason I like to do it is because you're so used to this in the real world, our perception is based off these fictitious. All right, is that good enough for today? Yep. Good work. We'll start chapter 7 next time. Sorry I didn't get to it today.
Did you send the email?
I sent the email about lab?
Yeah.
Yes, I sent it on break. Check for it right now if you want.